Let's do an example of finding the flux. Okay? So here we're going to find the flux of this vector field, x, y, z, across the helicoid, which is parameterized by u cosine v, u sine v, v, where u goes between 0 and 1, and v between 0 and pi over 2. Right? So if you're not familiar with what a helicoid looks like, it's going to be kind of hard for me to draw here, but imagine kind of like a spiral ramp, right? Or one of these spiral pasta things, right? So it kind of looks something like that. Okay. So when doing this, we need to find, well, we already actually have the parameterization in this case, so really we just need to get the correct orientation and then set up and do the flux. All right. So for finding the orientation, we need to take these two derivatives, Ru, which is u cosine v. Oops, sorry, it's just cosine v. Whoops. Right. Cosine v, sine v, and 1, and then Rv, which will be negative u sine v, u cosine v, 0. I did that backwards. This one's 0. This one is 1, because that's a v, not a u. So Ru is cosine v sine v 0. Rv is negative u sine v, u cosine v 1. All right. So what order do we take the cross product in? Again, you can figure this out by looking at grid lines if you wanted to, or you could just take the cross product. So I'll describe in words right now what the grid lines one kind of means, and then we'll just do the cross product. Right? So here, the grid lines for u extend from the z-axis outward along the helicoid. Right? So the helicoid's this thing that's kind of spinning like this as you go up. And the u are just these radial lines. Kind of like, imagine if you have a spiral staircase tracing out the steps. Right? It would look something like that. Rv, in this case, since v is kind of telling us how we're rotating, the grid lines for v are just kind of spirals that go up. They start kind of really close to the z-axis, and then they just get bigger and bigger. Right? So if we use that, we see Ru points along that radial direction, Rv points in the direction of the rotation. So if we do the cross product, Ru cross Rv, we'll get the upward orientation, because it's that same right-hand rule stuff, where you put your hand out along the first direction, curl it towards the second, and then your thumb points up. Okay? So that's how you can figure this out. But if that didn't make sense to you, or you don't want to think about that, just pick an order, do the cross product, and go from there. Right? So this cross product, this will be sine v, negative cosine v, and u. Okay? So this will be the cross product here. At this point, I'll let you just check that that's the right one. All right. So is this the upward orientation? Well, upward means the k component or the z component has to be positive. And since u goes from 0 to 1, we can see here, yeah, this is always positive, so this is the right one. Now here's the nice thing about computing flux integrals. We don't need the magnitude of this guy, so we're done with this. Now we can just plug this parameterization into f, do the dot product of that with this, and then integrate. Much better than the other surface integrals, I think. All right, so f of r of uv. Okay. So, well, that's just x, y, and z, so that actually looks just like the parameterization. Here's x, plug it in there. Here's y, plug it in there. and here's z, plug it in there, right? So then what we need is f of r of uv dot product with ru cross rv, right? So it's this dot product this, so u cosine v sine v, okay, plus this dot product with this, so negative u sine v cosine v, right? And then this dot product this, plus uv, okay? All right. Well, this and this just cancel, so we're only integrating uv over the surface now, right? So the flux, which is this double integral s f dot ds, right? This is simply given by integrating uv, let's say du dv, because the region of the domain of the parameterization is just a box. So u goes from 0 to 1, v goes from 0 to pi over 2, right? And then when we integrate this, we're going to get pi over 8, right? Again, I'll let you double check that that's the right answer. It's not the right answer. It's pi squared over 8. So you can think of this, we're integrating both of these and getting a half out of it, right? Actually, I've done it wrong again. It's not even pi squared over 8. It's pi squared over, let me just show you. I've said it wrong enough times. So it's pi squared over 16, by the way. Oops. So when we do the first integral, u, so we get 1/2 u squared v from 0 to 1 dv. So that's where we get the first a half from. Right, and then we just have v dv left. Integrate that. Oops. Keep writing these integrals. Right. Integrate that, and we get another 1/2 v squared from 0 to pi over 2. So that's 1/4 of pi squared over 4 minus 0. So pi squared over 16. Right? So that's the answer. Right? So again, flux integrals really aren't so bad. Right? Hopefully this made sense. Hopefully the process of computing a flux integral makes sense and isn't too bad. And see you in the next video.